We got angle A, QNR is equal to 180 degree, and this triangle we got 180 degree. Comparing these equations, removing this QNR, you got R1 plus R2 is equal to A. The total deviation delta is a sum of deviation at the two phases. We got sigma, or its delta, is equal to I minus R1 plus E minus R2. So this is the equation. From there, delta is equal to I plus E minus A, replacing your R1 and R2. Thus, the angle of deviation depends on the angle of incidence. A plot between the angle of deviation versus angle of incidence is made. You can see that in general, any given value of delta except for I is equal to E correspond to two values I and hence of E. You can see it here. This in fact is represented from the symmetry of I and E. This is the equation. So delta remains the same if I and E are interchanged. We don't have any problem. Physically, this is related to the fact that a path of ray is depicted over here and we trace back, resulting in the same angle of deviation. At the minimum deviation dm, the refracted ray inside the prism becomes parallel to its base. We have delta is equal to dm, I is equal to E, which implies R1 is equal to R2. So R1 equal to R2, R1 plus R2 is equal to A, which indicates that 2R is equal to A and R is equal to A by 2. In the same way, equation 2 gives sigma is equal to I plus E minus A. Replacing a sigma with dm and I with E, you got dm is equal to 2I minus A. So I is equal to A plus dm divided by 2. If we talk about the refractive index of the prism N21, which is nothing but N2 by N1. So replacing the value of N2, that's sine A plus dm by 2 and sine A by 2. The angles A and dm can be measured experimentally. So equation 5 thus produces and provides a method of determining the refractive index of the prism. For a small angle prism, a thin prism dm is also very small, and we get, so N21 replacing a sign, removing the sign, you get A plus dm by 2 divided by A by 2. So dm is equal to N21 minus 1 into A. It implies that thin prisms do not deviate like much.